Section 7 will be the last section we have for this chapter, and we're going to look at the applications to business because this is business calculus. So first, let's kind of look at consumer and producer surplus. Here you can see on this graph that there's a demand equation and a supply equation for a product, and we got to figure out what is which. Well, the demand curve is your one that is decreasing. Lower prices are associated with higher quantities demanded. Higher prices are associated with lower quantities demanded. Your demand curve are often shown as if they were linear, but there's no reason they have to be. The supply curve is increasing. Lower prices are associated with lower supply, and higher prices are associated with higher quantities supplied. The point where the demand and the supply curve cross is called your point of equilibrium. So here we have our demand curve, and then here we have our supply curve, and then right here at this point where they cross, that's our equilibrium point. And so if we come down here and we look at our graph in a different light, you can see we have our demand and our supply, but where is our surplus? Well, here's our consumer surplus, and that's where we have more product out there than they're demanding. And here is our producer surplus, where we have more product than they are wanting as well on our end. And so looking at a graph and figuring out where these areas exist is problems that we're going to face. So suppose that the price is set at the equilibrium price, so that the quantity demanded equals the quantity supplied. Now think about the folks who are represented on the left of the equilibrium point. The consumers on the left would be willing to pay a higher price than they ended up having to pay so that the equilibrium price saved them money. On the other hand, the producers represented on the left would have been willing to supply these goods for a lower price that made more money than expected. Both of these groups ended up with extra cash in their pockets. So graphically, the amount of extra money that ended up in consumers' pockets is the area between the demand curve and the horizontal line. This is the difference in price summed up over all the consumers who spent less than expected to a definite integral. So we're going to note that since the area underneath the horizontal line is a rectangle, we can simplify the area integral. And so you're going to see that here. And so the amount of extra money that ended up in producers' pockets is the area between the supply curve and the horizontal line. This is the difference in price summed up over all the producers who received more than they expected, similar to your consumer surplus. This integral can also be simplified. And so here's a nice little yellow box to help us with this. Given a demand function and a supply function and the equilibrium point, the consumer surplus is going to be, let's note some key things here. This is between 0 and the x value of your equilibrium point. And this is looking at your demand function and your supply function. The producer surplus looks like integration by parts, but also a definite integral. And then we can see that the sum of the consumer surplus and producer surplus is your total gains from trade. And so we're going to use this yellow box as we work through some of these situations. And so what are our units going to be? If you were doing price per item times quantity of items, and so that would be the money would be your unit because the items are canceling out. So let's kind of play around with this idea or situation that's been given to us. And so it says, suppose the demand for a product is given by P equal to D of Q equals negative 0.8 Q plus 150, and the supply of the same product is given by. So here is our demand equation, and here is our supply equation. For both functions, Q is the quantity and P is the price. So first we want to find the equilibrium point. To find the equilibrium point, we're just going to set those equations equal and we're going to solve, because that's where those two functions are crossing on your graph. And so I'm going to add the 0.8 Q to both sides. And that gives me 150 equal to 6Q, and then divide by 6. So this gives me Q equal to 25. And so that's going to be our x value. Now, in order to find that, since it's in both equations, we can go into either of them and figure it out. So that's going to be 5.2 times 25 in order to figure out our P. And so you're just going to type that in your calculator. So 5.2 times 25 gives us P to be 130. And so this is going to be our equilibrium point with the product. Now, for B, we want to find the consumer surplus at the equilibrium point. So in order to find the consumer surplus, we're going to use this equation up here, and let's kind of work through that with the data that we have. So we are looking at the definite integral from 0 to the x value of our equilibrium point, which was 25. Then it says that we need dq. And so that means we need our demand equation, negative 0.8q plus 150 dq, minus the x and y value from your equilibrium point, or they call this q star and p star or asterisk, and so multiply those two together. So we'll say 130 times 25. And so this is going to be the setup of our problem. So working this out, we can see that since this dq stopped here, this is the only part we're integrating, and then we're going to subtract off that 130 minus 25, or 130 times 25, excuse me, which is a value of 3250. And then we're going to integrate this, so this is negative 0.8q squared over 2 plus 150q, integrate it from 0 to 25. You can see plugging in 0 wouldn't give me any value, so I'm just going to plug in 25 into that function. So we're at negative 0.8 times 25 over 2. Make sure we square that 25, plus 150 times 25, and then subtract your 3250. This will give you a total value of $250, and that is your consumer surplus. In order to find your producer surplus, we're just going back up to that yellow box. First, you multiply your equilibrium two values together. So that's that 130 times 25 minus, now you integrate from 0 to 25 of your supply equation, which was 5.2q dq, and then we're going to work this problem. And so we already know this is 3250 minus, we're going to do 5.2 q squared divided by 2, integrate from 0 to 25. And again, that just ends up giving you 3250 minus, plug in the 25 because plugging in 0 would not give you a value. So 1625, and then subtracting those, you get 1625. And so that is your producer surplus. And so although these equations up here look kind of crazy, breaking it down, this Q star is just when you have that equilibrium point, they call that first value Q and P. So that would be to this X value here, and you can see that in this equation. Here is your demand function, and you're going to integrate with it. And then right here, you're just going to multiply these two values together. Now, in the other one, you multiply the two values together first, minus the integration of integrate from 0 to that Q value of your supply function. So again, that was really confusing with all the D's and Q's and whatnot, but hopefully through this example, you can kind of see how we got that data. But again, it goes back to just applying all these definite integrals. So if you're still struggling with integrals, please reach out at this point and let me help you. Example number 2 says, the table below shows some information about the demand and supply function for a product. For both functions, Q is the quantity and P is the price in dollars. So part A, it says which is which. That is, which table represents your demand and which represents your supply. Since the first table shows a decreasing price associated with an increasing quantity, so remember, Q is your quantity, P is your price. You can see that this price is going down as our quantity is going up. And so therefore, the first table is going to be our demand function. Part B says, what is the equilibrium price and quantity? So let's look at this. For both the functions, when we look at this, Q to be 400, you can see we have the exact same value, just like setting those equations equal. So when the quantity is 400, the price is 40. So that means the equilibrium price is $40 and the equilibrium quantity is 400 units. But notice that we were lucky here because the equilibrium point is actually one of the points shown. In many cases with a table, we would have to estimate. And so it's better working with your equations that you could solve exactly, but this one worked out really nice, and that's why I want to show you it in a table. Part C says, find the consumer and producer surplus at the equilibrium point. And so that's what we need to look at here. So remember, the consumer surplus uses the demand equation, and that comes from the first table. And we're going to have to approximate that value of the integral just by using rectangles. And so there's 4 rectangles that you could use, and you could use your Riemann sums to get there. And we didn't really focus on those Riemann sums, but I just want to kind of set this up for you so you can see what's working out with it. So if I want to do the consumer surplus, we're going from 0 to 400 because our equilibrium point was at 400, 40. And then you're going to do your demand equation, whatever it may be, dq, minus multiply those two together. So I want to show you that setup. Now, if you're just doing the basics of this, going back to kind of your Riemann sums, what you do is you start multiplying the length and width of your rectangles and add all those up and then subtract it out. This one actually turns out to be 7,000 when you go through that entire process. But again, I wanted to show you just some basics with the table, and then the problems we're going to face in the homework are going to be more equations and exact answers where there's no having to estimate on values. So let's also kind of wave our hands at this producer surplus. Now your producer surplus uses the supply function, and that comes from your second table. This was our supply function. So again, you would have to set up Riemann sums like we kind of waved our hands at and discussed, but again, let's just do some basics. This is where you multiply your 40 times your 400 on the front end and then subtract off from 0 to 400 of your supply function being integrated with respect to Q. And that gives you approximately about 6,400. And it goes back to, again, basics of setting up rectangles and kind of working through them. But again, on the table, I just wanted you to be able to see demand tables, supply tables, and how you perchance could find the equilibrium or even use your surplus equations. The next part of this session, we're going to kind of revert back to some algebra skills that you should already kind of have within your knowledge. If you've had any classes before this, such as the business class or an algebra class or pre-calc class, you'll recognize these functions as we go. We want to kind of remember, how do we calculate compound interest formulas? How do we compute continuously compounding formulas? And these are formulas I assume or want to expose you to remind you of how to use them. So there's our compound interest formula. Here's our continuously compounding. You can see it reverts over to E. And let's review what these values mean. P is going to be your principal or initial investment. R is your annual interest rate written as a decimal. And A of T is the amount in the account at the end of T years. If you're using these formulas to find out what an account will be worth in the future, such as when your T is greater than 0, and then A of T is called the future value. And if you're using the formula to find what you need to deposit today to have a certain value P sometime in the future, they call that the present value. So I just want to make you aware of some of these words and kind of remind you of things that you already know. These are really simple equations where you make a single deposit into an interest-bearing account and let it sit undisturbed, earning interest for some period of time. But you also have learned, probably through other courses and other sections, that more complicated and annuity formulas deal with slightly more complicated situations where you make equal deposits, equally spaced in time. But again, real life is not so always neat. Now, where does calculus come into play with this? Calculus allows us to handle situations where deposits are flowing continuously into an account that earns interest. As long as we can model the flow of income with a function, we can use a definite integral, like you've seen in all these examples we've been doing, to calculate the present and future value of a continuous income stream. So continuous income stream is what we're looking at here. The idea is each little bit of income in the future needs to be multiplied by the exponential function to bring it back to the present. And then we'll add them up, all up. And so if we're adding up all those values, that's where that definite integral comes into play. So Here it is defined. Here's your nice yellow box to go with this. A continuous income stream is, suppose your money can earn interest at an annual interest rate of R, so same variable, compound it continuously, so we're going to have to use our e to the RT. Let f of t be a continuous income function in dollars per year that applies between year 0 and year t. Then the present value of the income stream is given by this function here. We're going to go from 0 to t of our function times e to the negative RT. Then your future value can be computed by the ordinary compound interest formula of p e to the RT like you're used to seeing. So this is a really useful way to compare two investments and find the present value of each to see which one is worth more today. That all might sound a little confusing, so let's kind of just jump into an example here and see what we can do. And so here's our example. It says you have an opportunity to buy a business that will earn $75,000 per year continuously over the next 8 years. Money can earn 2.8% per year, compounded continuously. Is this business worth its purchase price of $630,000? And so first note that we still have to make some simplifying assumptions. We have to assume that the interest rates are going to remain constant for that entire 8 years. We also have to assume that the $75,000 per year is coming in continuously, like a faucet dripping dollars into the business. Neither of these assumptions might be accurate. But moving on, the present value of $630,000 is $630,000. This is one investment where we put our $630,000 in the bank and let it sit there. So to find the present value of the business, we think of it as an income stream. The function f of t in this case is a constant $75,000 per year. And so we would say f of t is equal to $75,000. The interest rate is 2.8%, and the term we're interested in is 8 years. So my rate is going to be equal to 0.028, changing it to a decimal. And my time, where we use a capital T, is 8 for 8 years. So the present value would be equal to the integral from 0 to 8 of 75,000 e to the negative 0.028 t dt. And so we just need to integrate this and then find our values. And so the integration of this would be 75,000 e to the negative 0.08 t. So 75,000 just stays where it is. The integral of e is just e. Divide it by what the derivative of that would be, which would be negative 0.028 using our u substitution. We're going to integrate this from 0 to 8. Plugging in those values and subtracting them using your calculator, you get 7672,511.66 because we're dealing with money. So the present value of the business is about $672,500, which is more than the $630,000 asking price. So this is a good deal. So let's do another example and look at using these present value, future values kind of formulas. It says a company is considered purchasing a new machine for its production flow. The machine costs $65,000. The company estimates that the additional income from the machine will be a constant $7,000 for the first year, then will increase by $800 each year after that. In order to buy the machine, the company needs to be convinced that it will pay for itself by the end of 8 years with this additional income. Money can earn 1.7% per year, compounded continuously, should the company buy the machine. And so we'll assume that the income will come in continuously over that 8 years. We'll also assume that the interest rates will remain constant over that 8-year time period. We're interested in the present value of the machine, which we will compare to its $65,000 price tag. So we're going to let t be the time in years since the purchase of the machine, and the income of the machine is different depending on the time. From time equals 0 to time equal to 1 the first year, the income is a constant $7,000 per year. So we see that the company estimates the additional income will be a constant $7,000 for the first year. So from t equals 0 to t equal to 1, it's bringing in the $7,000. From t equals 1 to t equal to 8, the income is increasing by $800 each year. They will increase by $800 each year after that. the income flow function then would have to be f of t is equal to 7,000 plus 800 t minus 1, because in that first year we didn't have that 800. And so then that would give me 6,200 plus 800 t, just distributing and combining like terms. So to find the present value, we'll have to divide the integral into two pieces, one for each of the functions. So we're going to have to integrate first from 0 to 1 of 7,000 e to the negative, let's see, our rate was 1.7%, so r is 0.017. So negative 0.017 t dt, plus we're going to integrate from 1 to 8 when it will increase by $800 each year. And that function was 6,200 plus 800 t, that's our f of t, e to the negative 0.017 t. And then we need to find these values. So I'm going to integrate the first one. That would give me 7,000 e to the negative 0.017 t divided by negative 0.017, again, using a u substitution to help me with that integral from 0 to 1. Plus, we would have to multiply this out. Let's just look at that integral there. And so I'm going to distribute this e into here so I can separate that out. So I get 6,200 e to the negative 0.017 t plus 800 t e to the negative 0.017 t, that whole thing dt. Now this is why we had to cover so many integration techniques previously to this section, because now, okay, so in my first one, bring it down, we have 7,000 e to the negative 0.017 t divided by negative 0.017. We're going to integrate that from 0 to 1. This next piece is going to react the same way. So plus 6,200 e to the negative 0.017 t divided by negative 0.017, integrated from 1 to 8. And then this last part here, because this is a product of the two functions, we're going to have to do integration by parts. And so we're going to move over here. I'm going to switch colors on you, and I'm going to pick my u and dv. Remember, you want to pick your u if it doesn't have an ln to be the part that if you took the derivative of it, it would go down. So its derivative would be 800. dv is going to be that e to the negative 0.17 t. So if I integrate that, as we've done on the previous two parts, that would be e to the negative 0.017 t divided by negative 0.017. So remember your formula, uv minus the integral of v du. So that's going to be plus, and again, I'm just doing this section here now, uv, so that's 800 t e to the negative 0.017 t divided by negative 0.017 minus the integral of v du. Now with v, I'm going to go ahead and write the negative 0.017 t. Let me go ahead and move up that formula here so we have some space. I'm going to put that divided by negative 0.017 out front there as a coefficient. And then du is 800. And so that gives me this value. And so I'm going to put these two negatives together to give me plus and leave that coefficient out front. And so the integration of that piece would end up with, here's our final result, well, of our definite integral, so we can actually plug in all these numbers over negative 0.017. We're integrating that from 0 to 1, plus 6,200 e to the negative 0.017 t over negative 0.017 from 1 to 8. We've got this piece here, 800 t e to the negative 0.017 t over negative 0.017. That's integrating from 1 to 8 as well. And then plus 800 e to the negative 0.017 divided by 0.017 negative, and that's just the integral. And we already have a 0.017 here from the udv, and it's integrated from 1 to 8. Now the only way that I would probably clean this up is I would probably just use these three values together and combine You could possibly combine the first and last, but I would just leave these three all together and plug in 8 into the 3 terms, get your answer. 1 into the 3 terms, get your answer. And then also combine it with this. Now all of this together, because the rest of this would be calculations with your definite integral, gives you a value of 70,166. And so if we go back to the problem and say, you know, will this value, the present value, is going to be greater than the cost of machine, so this company should buy this machine. So these are definitely, you have to remember, we are in section 7. This was like the culmination of definite integrals, use substitution, integration by parts, and then the business application. So in an exam sense, I can't give a ton of these. These take a while, and it's tedious with the details. But I would encourage you, as you work them out, to show all steps. Contact me if you need assistance. I'll be happy to either meet with you face-to-face or on Zoom, or to possibly work one of the homework problems out for you if you need kind of to see that step-by-step as you do in example problems. But just reach out, because this is going to be the application of all that we've been working on in this chapter. So hopefully this kind of pulls your concepts together and does not overwhelm you, because I know this problem could. Look at all that work we just did. But just reach out if you need some assistance as you go through.